Good morning, everyone, and welcome to today's seminar. My name is Xinwei Mao. I'm an assistant professor in the Civil Engineering Department at Stony Brook University. Today, I'm very glad to have this opportunity to share with you the findings in a recent project that the center has finished on the topic of impact of lexine nitrogen on nutrients removal for on-site wastewater treatment. I'd like to divide my talk to several parts. So I will first provide you a background, and I will talk about the case studies we finished and discuss the results. So at first, we want to know why we care about lexine nitrogen. So we know the global flows of reactive nitrogen have increased significantly over the past century in response to land use change, agricultural intensification, and elevated atmospheric nitrogen deposition. So the excess nitrogen flows to the coast will cause algal growth, and it will disrupt the aquatic ecosystems and negatively impact the coastal economics. We know US EPA has established a very aggressive nutrient reduction goals to achieve water quality objectives for the coastal regions in a wide range of measures, from upgrading of wastewater treatment plants to implementation of farm-level best management practice in order to reduce the nutrient from the flows to different coastal regions. As we show in this map, you can see the regional trends in nutrient and sediment loadings to the major coastal waters during 2002 and 2012. We can see the trend of nitrogen loading decrease in certain coastal zones. However, although widespread implementation of these measures and notable reduction in nitrogen inputs were observed, still we So we still see the nitrogen concentrations in surface waters are in many cases remaining steady. So one of the reasons for this phenomena is the presence and the abundance of the lexine nitrogen present in the groundwater and in the sediment. So by definition, lexine nitrogen is the nitrogen that has accumulated in groundwater and other storage areas. So here I want to show you a few cases that the lexine nitrogen has contributed significantly to the current nitrogen loading. So the first example is the Gulf of Mexico. So as we can see, the nitrogen sources in the Gulf of Mexico, the majority of it is from agricultural practices. So there was a study published in 2018 in the Journal of Science. So in the study, the researchers, they used historical data and also applied a model to estimate the contribution of lexine nitrogen to the overall nitrogen loading in the future. So they found back in 2010, almost 50% of the catchment nitrate load was made up of lexine nitrogen that has already resided in the area for more than 30 years. And even if the agricultural nitrogen use became 100% efficient, it would still take decades to meet the target nitrogen load due to the presence and the huge quantity of the lexine nitrogen. So another example is the Chesapeake Bay. So since 1980s, the Chesapeake Bay program has worked to implement a wide variety of measures to reduce nutrients flows to the bay. We can see for the nitrogen sources, there's a variety of different nitrogen sources. And in a recent study published in, I think in 2019, so the researcher found a significant accumulation of groundwater nitrogen in Chesapeake Bay watersheds comes from lexine nitrogen. And it accounts for as much as 50% of the annual nitrogen loading in some of the watersheds. So in terms of achieving this nitrogen reduction goal, so we have to estimate a times of order of decades time lags in order to achieve that. So if we look at Long Island, so where are we in terms of lexine nitrogen presence and quantity? So in this slide, you can see basically, according to a previous study, in Long Island, Great South Bay, almost 70% of the nitrogen source comes from the on-site wastewater treatment units, so as a septic tank and cesspools. So for a current septic tank and a cesspool, it includes a concrete leaching ring with holes on the side and no bottom. So for Suffolk County and Nassau County, we have about over 510,000 these type of systems. So it is critical for us to upgrade these systems to sustainably and effectively remove nitrogen in order to reduce the nitrogen loading to the coastal regions from such systems. So, and also this is one of the essential goals of the center. So on the other hand, we're also very eager to understand how much of the nitrogen loading is actually from the laxing nitrogen that are present surrounding the pool, beneath and surrounding the pool, especially considering the shallow water table and also the shallow depths of the leaching pools currently reside. So in this slide, I want to show you a map of the estimated depths to the water table. So this is the data published by the USGS back in 2010. And you can see the color zones, especially the red colors, indicate the regions that the water table is less than 11 feet. So basically, the laxing nitrogen we know laxing nitrogen will be constantly leached out due to major storms, raining, and flooding events. And due to the global warming events, more and more laxing nitrogen may be leached out due to the sea level rise. So this becomes a challenge in reducing nitrogen loading to these coastal groundwater. So the question becomes, what do we know about the current laxing nitrogen presence in the cesspool and leaching pools? So unfortunately, we know Unfortunately, we know very little about the amount, composition, and the fate of laxing nitrogen remaining in the soil surrounding the current cesspools. So if you search the keywords of cesspool or leaching pool or on-site wastewater treatment system and laxing nitrogen, it is very hard to find any results in the searching engines. And on the other hand, we know very little about geochemical and environmental effects on the laxing nitrogen presence and their quantity. So these leaching pools is much more like a black box. So we know the wastewater comes in with organic nitrogen, organic carbon, with some level of removal mechanisms, and it will be leached out to the subsurface. So some factors such as the presence and a quantity of organic matter, the soil types, and like temperature or pH impact on the level of laxing nitrogen presence is ill-defined. So we come up a few questions then, and we hope we can address these questions in the proposed study. So the first question we want to know is, how much laxing nitrogen is in the soil surrounding a current leaching pool? The second question is, what is the composition of this laxing nitrogen? And how would these environmental conditions, such as the soil matrix properties, impact the level of laxing nitrogen? We also want to know how would new on-site wastewater system installations, such as the proprietary or non-proprietary system installation, would affect the level of laxing nitrogen release to the environment. And the last question we want to address is, how would natural phenomena such as the rains, storms, would affect the laxing nitrogen release to the environment? So in order to address these questions, we conducted a case studies. So the following slides I'm going to describe has already been published in the 2020 in the Journal of Water Research. So the details of this study, you can request electronic version from us, or you can search it online. So in this case study, we have 3 research objectives. The first one is to investigate the level and the composition of laxing nitrogen remaining in the soil matrix at 2 pH conditions. The neutral pH represent the leaching pools currently in use, and low pH represent the pools has been acid washed or has been abandoned after acid wash. The second research objective is to evaluate the effect of soil matrix properties on the nitrogen absorption capacity. The last one is to determine the extent of nitrogen leaching under different environmental related scenarios. So based on these 3 research objectives, here is a summary of the workflow of the study. So at first, we identified 2 study sites, and at each site, we collected soil coring samples and conducted physical and chemical analysis. Based on the information, we further evaluated the lectin nitrogen quantity and composition at these 2 different sites, and we conducted leaching experiments to estimate the lectin nitrogen leached from the 2 sites at different scenarios. So in the following slides, I'm going to describe each of these parts. So at first, we identified 2 study sites in this study. So these 2 sites consist of single-family homes utilizing concrete leaching pools. And these leaching pools are representative of typical on-site wastewater treatment systems in Suffolk County. So based on the Google map, you can see the circles indicate the location of the leaching pools. And we can see actually both sites are close to the Great South Bay. And we expected to see shallow groundwater tables. The arrows here indicate groundwater flow direction. And at site A, the pool was receiving wastewater and had a neutral pH, while at site B, the pool had been acid washed to alleviate a pipe clogging issue before the sampling event. So now let's look at where we sampled our soil matrix. So at sampling site A, we collected 4 coring samples. The first one, we call it A1, is the sample right beneath the pool. So here is the ground surface of the pool A, and with the groundwater flow direction. And here indicate the water level in the pool. And there's a very shallow water layer on the top of the sludge layer in the pool. So we collected this soil sample right beneath the sludge layer. And the next sample was right next to the leaching ring. And the third sample was collected 1 foot away from the second sample. And last week, got another reference core sample up gradient from the pool to represent the background nitrogen concentrations. So the reason that we collect these 3 samples is based on the hypothesis that the majority of the lectin nitrogen would present beneath the pool, because we think the water will be slowly filtered through the soil due to gravity. At the second location, site B, we were able to collect 1 sample right beneath the pool. So we call it B1. And for all the samples we collected, we dissect them to several sections and conduct analysis of each of the subsamples. So this slide shows you a couple of photos that we took while we do the sampling. The first one you can see here is the A2, that is the sample right next to the leaching ring, and A3 is the 1 foot from the second sample. So here is the geoprobe, the sampling device we used. And at the site, after we took the sample out from the ground, we dissect the samples right away and put them on ice and transport them back to the lab and conduct analysis immediately. So this photo shows the reference core, the A4. You can see actually from the color is actually the majority of the soil is sand. And these 2 photos shows you the air-dried sample after we took the samples back to the lab. And these blackish color indicate the samples collected beneath the pool. So next, let's look at the results and discussion part. So at first, we conducted physical and chemical analysis of all the core sample. It's a very busy table. You do not have to look into the details. I'm going to walk you through them. So you can see the highlighted cells are actually from the A1 and B1. So these are the 2 samples collected beneath both pools. So, and the rest of the cells indicated the samples collected from site A. So based on, first of all, we conducted the particle size distribution analysis. And from this green size distribution, we found the samples collected beneath and surrounding the pool showed a uniform composition, with the majority of the samples consisting of sand, and with a very small amount of gravel and the clay and silt. So these indicate the soil type is loam sand soil type. The moisture content here, you can see actually beneath the pools, we saw much higher moisture content and almost near to saturation. And these are much higher than the samples we collected surrounding the pool. This is due to the continuous application of wastewater to this pool. And in terms of pH, the neutral pH was observed in the cores collected beneath and surrounding pool A, and while the cores collected beneath pool B showed acidic pH. And in the next few slides, I'm going to talk about the total organic carbon, total lactic nitrogen, and total inorganic nitrogen in those soil samples. And I just want to point out here that here shows you the total inorganic nitrogen ratio in the total lactic nitrogen. We can see the majority of the lactic nitrogen present in those soil matrix is in the organic form, since the inorganic nitrogen only accounts for less than 5% of all the samples we collected. Okay, so now let's take a look at the presence and composition of the total lactic nitrogen in all the soil samples we collected. So in this figure, the x-axis is the total nitrogen per gram of the dry soil, and the y-axis is the depth of all the sampling from 0 to 6 inches to 18 to 24 inches. So in this figure, we can find the highest total lactic nitrogen level was observed at the first 6 inches beneath the pool. As the sampling depth increased, the lactic nitrogen level decreased. And when we compare the samples collected beneath the pool and in the surrounding soil, we can compare the A1 to the A2, A3 to A4 samples, and we found that the TN levels decreased as the sample radial distance increased from the pool. And when we compare the two different locations, site A and site B, although the soil pH was different, there was no statistically significant difference in the TN level beneath the pool at each depth. So with this measurement, we were able to calculate the estimated lactic nitrogen level beneath the pool. So before we do the calculation, we also compare our observations with different soil types and see how would our lactic nitrogen level compare to agricultural soil and wetland. So from this table, you can see the lactic nitrogen stored beneath the pool is can be a nitrogen source with the potential similar to the agricultural soil and the wetland environment. But these levels are much higher than the residential soil without any nitrogen loadings. So with a current leaching pool, if we define the controlled volume to be beneath the pool and also with these 1 foot away from the bottom, from the leaching ring, and with the measured soil density and with the assumption of the typical wastewater concentration in the domestic wastewater, and also with the minimum design wastewater flow rate, we were able to calculate how much of the lactic nitrogen has been stored at site A and site B. So basically, with all the information and measurement, we can calculate the total lactic nitrogen at site A is about 2.2 kilogram. And 87% of this lactic nitrogen was present beneath the pool. For the site B, the total lactic nitrogen is comparable, is 1.9 kilogram nitrogen. So if we scale it up and to calculate for the 340,000 leaching pools, roughly this number, in Suffolk County, we can get the total lactic nitrogen currently storage is around 714 tons. So with these experiments and calculation, so we were able to investigate this level and the composition of the lactic nitrogen remaining in the soil matrix. So next, let's look at how the soil matrix properties affect the presence and the capacity of the nitrogen absorption. So in the summary table, I showed a column of the TOC, the total organic carbon concentration in the soil samples. So we found the TOC levels present in the soil beneath the pool has a positive relation with the total nitrogen we observed in the soil matrix. So these correlations between the TOC and TN have been observed in samples collected at different agricultural sites. And this TOC to TN level in this study can be the result of the presence of domestic wastewater in the environment, because this TOC to TN ratio fell into the same range of the domestic wastewater. So basically, as the higher the total Lexi nitrogen we observed, that correlates to higher TOC levels. So when we look at the inorganic Lexi nitrogen present in the soil matrix, and we compare these levels from the different sampling locations, and we found that ammonium was the major form of the inorganic nitrogen present beneath the pools. So just to keep in mind that we are currently looking at a very small portion of the total Lexi nitrogen present, because the organic nitrogen actually is the major form of the Lexi nitrogen present in all the samples. So we also found that the ammonium is the major form of inorganic nitrogen with an NOx, which comprises of nitrite and nitrate. So they are present in the cores surrounding the pools and even further from the pools. So these increased NOx levels was likely due to a higher oxygen levels present in those surrounding soil and with less saturation. Another interesting phenomena we found is when we compare A1 and B1, so those samples were collected beneath pool A and pool B. We found a much higher ammonium levels in the pool A compared with pool B. So if we further look at the soil types difference and other geochemical factors difference, we found that the difference between these two sites is majorly pH difference. But in terms of the soil type, so we can see that for peat, clay, silt, and sandy soils, the ammonium absorption capacity can be in the range from 0.6 to 1.9. But for the silt and loam sand, which has low level of clays, the ammonium absorption capacity will decrease significantly. So in this study, we found the clay and the silt account for less than 3% of all the soil samples. So basically, the absorption capacity of ammonium is likely due to, mainly due to the presence of organic matter content in the soil. So as we know, when pH decreases, the cation exchange capacity will decrease accordingly. And also it will increase the competition of the hydrogen ions and the ammonium for the adsorption sites. So this would explain the higher ammonium adsorption level in the site A compared with site B. However, as I mentioned, the majority of the Lexi nitrogen is in the organic nitrogen form. So that means acid wash, although acid wash or low pH did affect the ammonium adsorption capacity, but it did not affect the overall level of Lexi nitrogen stored surrounding the pool. So since we observed such high, relatively higher level of total organic carbon, as well as the total Lexi nitrogen, so we were interested in the question whether there's any microbial biomass contribution to this Lexi nitrogen. So in order to answer this question, we extracted DNA from the soil matrix samples from the sample A1 and B1 beneath the pool. And with the DNA extracted, we estimated the levels of the microbial cells with assumption of the cell size and the density of the cell. So basically, in the last column of this table, you can see the number of the cells present at two sites were on the order of 10 to 8 cells per gram of soil. So this level was comparable for the typical grassland microbial cell density, which was also in the range of 10 to 8 cells per gram of cell. So with these cell density information and considering the nitrogen composition in microbial cells, we can estimate the Lexi nitrogen contribution from the microorganisms. So basically, we found the lectin nitrogen in the form of microbial biomass was negligible. Basically, less than 1% of the lectin nitrogen is from the microorganisms. So after these experiments, we answer the questions and finish the research objectives too. Basically, we evaluate the effects of the soil matrix properties on the nitrogen absorption capacity. So the next, we look at the nitrogen leaching potential from these soil matrix at different environmentally relevant scenarios. So the first scenario we selected is to use the soil matrix to leach the soil matrix using a synthetic aerobic treatment unit effluent. The reason we are doing this is when a current on-site wastewater treatment system is upgraded with an additional unit, we call it advanced treatment unit. In a lot of cases, it's a aeration unit which the aeration is provided for the septic tank effluent, and the BOD is degraded and nitrogen will be converted from ammonium to nitrate. So once such a system is added or upgraded to the current system, so the original leaching pool can serve as the final dispersal unit for this effluent discharge. So this option could help us to reduce the capital cost of excavating a new dispersal unit for the ATU effluent, and also could potentially be a more cost-effective option for the septic tank upgrade. So the question is, if we use this old cesspool as the disposal unit, will that lead to the release of lectin nitrogen to the environment? So in order to answer this question, so we conducted these leaching tests. So basically, these are the experimental setup. So we have the two desorption columns. We used the soil samples from site A and site B, and we packed these columns with the homogeneous soil samples to represent every 6 inches of the soil collected on site. And with the total lectin nitrogen measurement, we were able to calculate the total lectin nitrogen that were present in these two desorption columns. And also in this table, you can see with this level of total nitrogen, there's a very small amount of inorganic part, the ammonium, and there was the NOx level was under detection limit. So to conduct this desorption test, we first prepared a synthetic ATU effluent from the aerobic treatment unit. So this synthetic influent water contains a very low level of ammonium, a certain level of nitrate, and also we supply some calcium carbonate as alkalinity. So these levels were observed at some of our field size observations. So in regarding the operation conditions, so we first calculated the hydraulic conductivity of the soil samples based on our measurement of the particle size distribution as well as density. With the hydraulic conductivity, we were able to estimate the hydraulic retention time in both columns to be 35 to 41 hours, with the hydraulic loading rate at 1.2 gallon per square foot per day. So the desorption test lasted for 92 hours until the final effluent total nitrogen concentration equals to the influent total nitrogen concentration. That indicates no further nitrogen leaching happens. Okay, so here is the result of the time course leaching result of both columns. So as you can see for column A, as the synthetic ATU effluent passes through the column A, we found the TN concentration in the effluent reached the highest level at the first 12 hours and gradually decreased during the first 48 hours. And this reflects the elution of the pore water that were already present in the soil. And the nitrate concentration, very interestingly, the nitrate concentration, which is the triangle here, it the concentration decreased at the first 24 hours and then increased to the level close to the influent. And then after the 44 hours, this nitrate level decreased again and was under the detection limit. So accordingly, the pH after the 44 hours also increased. So this nitrate removal was possibly due to the heterotrophic denitrification. And because total organic carbon present in the soil can serve as the carbon source. So when we look at the column B, we found the TN concentration in the effluent was stable throughout the experiment. And after the 48 hours, both ammonium and nitrate reached the influent level, indicating no further nitrogen leaching occurred in this column. So also in the pH, we found low pH in column B, and this constantly low pH likely decreased abundance and activity of microorganisms in the soil, so there was no denitrification occurs in column B. So after the time course experiment, we calculated the accumulative level of lectin nitrogen that has been leached out from two columns. So you can see in this summary table, when we compare for this at scenario 1, compare the data from site A and site B, we found in site A, we eluted about 4 times higher of total nitrogen compared with site B. And this is possibly due to the reason that the absorption rate of the non-labile organic carbon would increase at low pH, and this will cause organic nitrogen in the column B to be more resistant to leaching. So the second scenario of the leaching test is to mimic the rain and the storm event. So we would like to investigate the effect of rainwater on the leaching of lectin nitrogen from the soil. So we conducted another round of leaching test using the soil samples collected at site A. And we want to compare the lectin nitrogen leaching performance at these two scenarios from site A. We first prepared a synthetic rainwater, which contains a very low level of nitrogen species and at a slightly acidic pH. So with the hydraulic conductivity, we calculated, and we can calculate the hydraulic retention time in the column based on the hydraulic loading we chose. The hydraulic loading we chose is based on the heavy rain event at 1.5 gallon per square foot per hour, and the duration of the test was 24 hours. It's similar to the scenario A. We stopped the experiments when we saw the final effluent TN was similar or equal to the influent TN, indicating no further leaching occurred. So here is the time course leaching results of the second scenario. So basically in the rainwater, there is very low trace cations and anions concentrations. So they have very little impact on the desorption test. So in the time course experiment, we found the effluent TN concentration increased rapidly and peaked in the first 2 hours, and then decreased to undetectable values after 12 hours. So these numbers indicating about 75% of the lectin nitrogen occurred in the first 4 hours. And when we look at the TN concentration and ammonium and nitrate concentration, we found the inorganic nitrogen accounts for about 40% of the lectin nitrogen leached out. Okay, so when we compare the result from two scenarios, so in this summary table, if we look at the soil source from site A and compare the result from scenario 1 and scenario 2, we will find the total TN leached out were comparable at these two scenarios, although they were at different flow patterns and different duration of the test. But when we compare the leached total nitrogen compared it with the total lectin nitrogen already stored in the soil columns, we found only a small portion, less than 10% of the leached nitrogen was leached out during the experiment. So this small portion of lectin nitrogen was majorly due to the strong physical adsorption of organic compounds to the soil particles. So after we conduct these leaching test, we would like to do some calculations and to see what are the implications for the leaching nitrogen leaching to the environment. So based on a previous study, the nitrogen loading to the subsurface water at Great South Bay, New York, was estimated to be this huge level for the atmospheric deposition. And for fertilizer, it is about over 500,000 kilo nitrogen per year. So we estimated for the current operating leaching pools or cesspools with the continuous wastewater replenishment, we estimated like how much total leaching nitrogen can be leached out from such pools with the assumption using the current average rainfall of New York State, and with the 77.5% of the total nitrogen can be leached out from the leaching nitrogen. So with all those information, we found that the total leaching nitrogen leached out from current septic systems is comparable to the contribution of fertilizers. And here I want to point out, this number is really a rough estimate, and the actual TN loading from our current leaching pools are heavily dependent on the weather condition. So if we have more rainfalls or the frequency and duration increases, we would expect to see more of the leaching nitrogen leached out from those systems. And what about the abandoned pools? Basically, we are talking about upgrading those pools with an advanced treatment unit and use the abandoned pools as the final discharging unit. So with our experiments and calculation, we found if we use those old cesspools as the final discharging unit, and with our leaching experiment, we found about 8.8% of the leaching nitrogen could be leached out over a period of 3.8 days. So that means about 62,000 kilogram nitrogen can be leached out if we replace all the old pools. But this would not happen immediately. This leaching nitrogen can be leached out over many years due to many reasons. So one reason is the slow leaching rate, or these organic compounds, they are very strongly absorbed to the soil particles. So the real leaching rate probably is lower than what we observed in the leaching experiment. And also, these leached nitrogen may end up in various coastal water bodies, not only to the Great South Bay, but also to also to the Long Island Sound, and also to some local watersheds. So let's see how our estimation are comparable to some other studies. So when we look into the literature, we found most of the leaching nitrogen leaching estimations were for agricultural soils. So here are two examples. So in a study that people look at the Mississippi River Basin, so they estimate the leaching nitrogen present in this agricultural soil will take about 35 years time to deplete. And in another study, when people look at the grassland soil, so they found the majority of the soil nitrogen was stable regardless of the soil texture, and leaching nitrogen would leach at a very low constant levels. So finally, I'd like to summarize what I just described in this presentation. So the first findings we got from this project is the level of leaching nitrogen accumulated beneath the leaching pools was comparable to the reported leaching nitrogen stored in the agricultural soil. The level of leaching nitrogen would decrease as the depth increase and the radial distance increase from the pool. We also found that most of the leaching nitrogen in the soil surrounding the pool is in the form of organic nitrogen, while the microbial biomass contributed to a negligible portion of the overall leaching nitrogen. And the major composition of the inorganic form of leaching nitrogen was ammonium, while the nitrite and nitrates level would increase as the depth and the lateral distance increase. The total leaching nitrogen accumulated in the soil beneath the leaching pools were estimated to be over 700,000 kilogram nitrogen for the over 300,000 households in Suffolk County. And this level was equivalent to about 17 days to 39 days of domestic onsite wastewater loading. Based on our leaching experiment, we found a small portion of the leaching nitrogen was leached out from the soil. And there was no statistically significant difference of the TN leached at two different scenarios or the pattern of the flow. So basically, that means the pattern, the flow pattern and the flow rate did not affect the level of accumulated nitrogen in the effluent. We also found pH has a significant impact on the nitrogen transformations in the soil. And it was possible that heterotrophic denitrification occurred during the leaching test, and they used the total organic carbon as the carbon source to facilitate these denitrification to occur. So at last, I want to just mention some limitations of this study and some of the future study directions. So in order to get a more comprehensive understanding of the leaching nitrogen presence, composition, and their impact on the nitrogen loading, we should increase the number of study sites. So we were also only able to sample 2 sites in this study. So whether they are representative to some other locations where the groundwater table are a little bit deep, and also how the leaching nitrogen really contribute to the certain watershed. We only sampled near the Great South Bay, so we do not know much about for the locations near the Long Island Sound. Also, the factors that impact the overall leaching rates need to be further investigated, because we know very little about the current operation conditions of those leaching pools. And also, the microbial process contribution to the leaching rate should be investigated for a more long-term experiment. And also, as I described for the amount of the total inorganic nitrogen ratio in the final leached leaching nitrogen, we found that the dissolved form of organic nitrogen accounts for over 50% of the leached leaching nitrogen. So how would that amount of nitrogen impact the receiving water is largely unknown. And with all the information collected from this study, how are we going to treat this leaching nitrogen to meet the water quality goals? Shall we add additional polishing unit such as wood chip bioreactors to take up the nitrate? Or shall we install the permeable reactive barriers to take up those leached out nitrogen? So those are the questions remained and can lead to future studies. So at the end, I want to acknowledge our collaborators and the people who have contributed to this study. As you can see, this is a collaborative effort. So Ms. Zara Malaki Sharaki, so she is a PhD candidate, and she led this project, conduct most of the experiments and write the paper. And Dr. Stuart Wah and Ms. Sarah Lotfi, they helped a lot in the experimental design and sample analysis. We also want to thank Dr. Hal Walker, Dr. Chris Gobler, and they helped us in this project from the start to the finalized paper. And we also want to thank Mr. George Hilfelder and Dr. Gilbert Hansen. So they helped us a lot while we discussed the how to conduct experiments and how to interpret the data. Also, we want to thank Dr. Roy Price and Ms. Zoe Smith. So they helped us in the sample collection and analysis. Also, Mr. Jonathan Wallace and Mr. Ronald Paulson from Suffolk County Department of Health Services. We had quite a few meetings to discuss how to best assess the samples. I also want to thank Mr. Brian Grogan from PWGC and his team. They did help us at both sides and help us to grab the samples and make it happen. So that's all for my talk today. And thanks for your attention. And especially thank you for attending today's seminar, given this extreme weather condition. And I'm ready to take any question. Thank you.
Thank you, Xinwei. That was a great talk. And thank you for your service to the center and your
Thank you.
scientific expertise that you bring to every project. It's very much appreciated. Um, so given your findings, I guess thinking about and there's remediation that could be done on any site, but maybe it's, and this is more of a value judgment call. What do you see as the relative value of addressing the legacy nitrogen versus going after new homes with new IA systems? And, you know, the relative, you know, I guess it's hard to estimate bang for the buck, but, you know, should efforts be made on going after this legacy nitrogen, or is it, you know, given we can't do everything all at once, does it make more sense to simply go after new homes and let you know, the legacy nitrogen be addressed at a later date, so to speak?
Yeah, that's a great question. So I think for in terms of like new homes, so definitely we recommend to install like new types of on-site systems without creating this problem, the legacy nitrogen. But for the current operating leaching pools and cesspools, or when we consider to upgrade these type of systems, we should consider the contribution of legacy nitrogen. So based on our observations from this study, we found, first of all, a very small portion of the legacy nitrogen could be leached out during the rain event or with the just effluent from the advanced treatment unit. But it's very hard to estimate how long this legacy nitrogen could be leached out. I think the significance of this study, one significance of this study is to help us to understand, so first of all, how much legacy nitrogen is there. With our estimation, it's comparable to the level of the fertilizers. So we can see like how much fertilizers contribute to overall nitrogen loadings. So basically, if we look at other contributions, such as the municipal wastewater treatment plant, so actually they contribute much more higher levels of nitrogen loading compared with fertilizers or these legacy nitrogen. But there's also like uncertainties regarding like how long this a quantity of nitrogen can be leached out. It can be sooner than we expected if we have more frequent rain events, or if you know, at the neutral pH, we probably can promote the microbial activities to leach the more nitrogen out of the system. So it's hard to answer, I mean, because there are so many unknowns, but definitely I think we just want to bring it to people's attention that, you know, legacy nitrogen is important. It is there, we cannot neglect that. We cannot neglect because it is under the ground and, you know, would not see them. So that would, you know, be I think that would be the most important part we want to bring to the scientific academia, yeah.
Hey, thank you.
Hi, good afternoon. This is Ken Ziegel with Suffolk County Department of Health Services. Nice job today. I had two questions. One, maybe just for a follow-up. Is there a reference for the 510,000 on-site sanitary systems versus, you know, we use typically around 380,000. I think in a different slide you were using 340,000. So I'm just kind of curious where the 510 comes from, but like I said, that could be a follow-up.
Oh, that is a rough estimate. Actually, the over 500,000, that was the both Suffolk County and Nassau County. So that is rough estimate. For the over 300,000, that is for Suffolk County alone.
All right, that makes sense.
Yeah.
And then my second question, and I don't know if this is appropriate given the small sample size, I'll call it, and the lab versus the field, but was any insight gained on what kind of rates of natural denitrification may have occurred at these sites or in these columns as the water kind of ran through the column? I thought there was a slide that talked about, at least for one of the columns, that it showed some natural denitrification, but I might have missed that.
That's a good point. Thanks for pointing out that. So let me just go back to the slides here. So I just want to mention for our leaching test, so both of the leaching tests were conducted in a relatively short period of time. So even if for the first scenario, or only conduct experiments for 92 hours, the second scenario only did experiment less than 2 days. So we use the criteria that the final effluent TN concentration is similar to the influent TN concentration. But I agree with you, there definitely would be microbial activities that would contribute to this nitrogen leaching from both conditions. I would say from our observations, at site A, where we saw neutral pH, at this condition, there probably will be more microbial activities occurred, not only during our leaching test, but for the long-term run, as more water comes through and will provide these dynamic redox conditions, and more of the organic nitrogen could be mineralized or be further nitrified from ammonium to nitrate, and denitrification may occur in the future. But for the site with a very low pH, we think this low pH would limit the abundance and activity of the microorganisms present in the soil. And definitely, as I pointed out at the end of the presentation, if in the future study, if we can extend the duration of the leaching test or get more samples from a variety of sites, it would definitely help us to understand better like how much these biological process would help the nitrogen leaching, and whether these are more representative to the real systems on the site.
Ken, just to jump in here, thanks, Xinwei, excuse me. Just to jump in to further address Ken's question, we do have some data from another project which looks at the transformations of nitrogen in a PSD, or at two sites, two PSDs that downstream of IA systems, and we'd be glad to share that data with you.
All right, sounds great. Thank you. And I would imagine that would any kind of leaching would vary, or natural attenuation would vary significantly too from site to site, and the age of the system, and like you mentioned, pH, and there's probably a million factors that go into it.
Soil type, very important.
Yep, agree. I thank you both.
Thank you.
Any further questions on today's presentation? People may be stuck staring at the snow.
Yeah, if you have further questions, also feel free to reach out to me or to the authors, and also reach out to the center. You can request any electronic version of our paper and so on. So if you have, we will be very glad to address those questions.